Good morning. It's me again, Shai. And welcome to the second class on sequences and transformers. So last week we started with recap of what we've learned with Asaf and the other instructors about processing images that are static. We started with a single neuron, a perceptron. We went to a convolution layer and built a convolutional neural network to process images. We saw that it's very efficient and very aligned with the way we perceive images. And last time, we expand our horizons to consider not only static images, but also things that are time-dependent, sequences like text, video, speech, and things like that. We talked about recurrent neural network. We talked about recurrent neural network with memory cell, the long short-term memory, LSTM, that actually helped training recurrent neural network when you have very long temporal sequences. And we conclude with attention block that actually says that you don't really need to do a recurrent processing of sequences. You can attend to everything. And it helps not only by aligning sequences in tasks like translation, but it also helps processing the sequence itself in the encoder or the decoder of the sequence. And this was very, very popular, and it gained a lot of attention in the realm of sequences and natural language processing. And when things are very successful, they propagate to other domains. So what we're going to see today is how this concept of attention circled back into the static realm of images and gave rise to the vision transformer. And this is going to be the focus of this class. Questions about what we talked about last time? No.
When you explained the transformer in the last time, I didn't really.
Yes, we will recap.
Okay.
Don't worry. Yes. Okay, but this is like the big picture, what we're going to do today. Okay. So we talked about the self-attention layer, which was the building block in the transformer architecture. And in self-attention, we have a single input, a sequence of tokens. And from this token sequence, we project it into query keys and values. And these are the trained parameters, the projection matrices that project each token into a query vector, a key vector, and a value vector. And the way we process the sequence is by each query asks, who's the most relevant key to me? This is done by computing dot products between the queries and the keys. It's like asking a question and checking multiple choice answers, the keys. And we normalize these similarities using a softmax functions to get probabilities, like the weights of the corresponding answers, the values. And then we sum the values based on these weights to get the output processed tokens. Okay? Yes?
So you describe that the softmax would be column-wise?
Yes, it's a column-wise. For each query, we compute a softmax over all the possible values. So it's the sum over values equals 1. It's a convex sum. Okay? And once we have this self-attention layer, we put it in a transformer block. The input to the block is a sequence of tokens. We normalize each token by a layer norm layer that we discussed in the fourth class. Then we compute the self-attention. We have skip connections over this block. Then we have another normalization and a multi-layer perceptron that actually projects its token to itself. So the tokens interact by the attention layer, and they are projected each on its own in the multi-layer perceptron block. And this is the transformer block, and a transformer architecture, as we saw before, is just stacking these blocks one on top of the other. And this is the basic architecture for GPT and all these very successful systems that we saw for natural language processing. It's highly scalable. It's easy to stack them. They are very simple. They work on parallel, so they don't need to process the sequence one token at a time. They work on a parallel on all the tokens. And the only thing that we saw last week is that we have some issue with the computation of the attention because it scales quadratic with the sequence length. Okay. This is a recap of what we saw last time on attention. Any questions? Yes.
How do you divide the NLP?
So I think they have two layers, one that increase the dimension and the other brings it back to the same dimension. I don't remember the factor, but it's, yeah.
Do you remind the importance of these skip connections?
So we saw that skip connections help propagating gradients. So if you propagate gradient through all the layers, each time you multiply by a matrix, you make a computation, the gradients are scaled, and then you need to worry that the gradient don't vanish or explode. But once you have a skip connection, you have like an express route for the gradients to go for all the layers at once. So this really helps stabilizing training. And it also proved very efficient in representation that you have skip connections. It allows you to do all kinds of skips and shortcuts during computation and training, regularize the system and things and so forth, but we don't get into this. Okay, so this is a very nice block. This is a very nice architecture. It processes sequences very efficiently and very successfully, and we want to take it into the domain of vision transformers, into images. And so what we're going to have in a vision transformer, we have an image, an input image. We have this multi-layer transformer encoder with these blocks of transformers, and now we want to process the image using the transformer. What's the problem?
No objective.
Objective is something that we can worry about later. First of all, how do we feed an image into an architecture that expects sequences? How do you put them together? Thoughts? Okay, so what we can do, we can actually artificially break the image into a sequence. So we take non-overlapping patches of the image, and each patch is now going to be a token in our sequence. And we have a sequence of patches that used to be an image. As we saw last time, the attention is permutation equivalent. So we want to make sure the transformer knows that these are not just a random collection of patches. There is an ordering here. So we add position encoding for the patches. So we project the patches into vectors by a linear mapping. So we have a linear projection. And then we add to each token position encoding code that says where in the image this patch came from. So if we shuffle the patches, the transformer would know that this is no longer an image, but a shuffled collection of patches. But once we have this sequence of tokens, we can process it with the vision transformer. This is not a problem. Yes.
The position encoding, shouldn't it be two-dimensional?
We'll get into this in a few slides. So we have a sequence of token. We put this sequence into the transformer layers, one layer after the other. Each layer projects these tokens based on their attention and their content. And we get a sequence of processed tokens at the end. Now we want to make a prediction of what's in the image. For instance, we want to do image classification. What's in this image? What we did in convolutional neural network, we had a pooling layer. We did some average pooling on top of all the feature map that we got. And then we got like a single vector representing the image, and we classified this vector. But we can do something that is slightly more elegant here. So we want to put some training, train some classifier on top of this representation that would give us a probability of one of these 1,000 classes of ImageNet. But we can do something that is more elegant than just averaging the tokens. If you recall, attention works with queries, the questions and answers. So we can ask a question, what's in the image? We can train a specialized token that is not part of the image, but is part of the architecture that actually asks the question, what's in this image? It's like a global token. What's in this image? And we process this token along with all other tokens in each layer. So at each layer, it asks what's in the image, sees the other tokens, and accumulates some global information. And by the time we process all the tokens through all the layers, we can discard all the other tokens that are patch specific. And we can look only on this global class token and ask what's in this image. Classify the image based on the content of this class token. Okay. And again, each block in this multi-layer transformer build is exactly the same as the transformer we saw before that was used to process sequences of text and language. So it's exactly the same architecture. The only thing we did here is to project the image into a sequence. So we created a sequence out of the image, and we used the same architecture and the same mechanism to process it as we would have processed a sequence of text.
How is it that giving it the numbers makes it not invariant with respect to permutations?
Because the numbers are added according to the position. So I have the patches, and I add the position based on their location. If I permute them, I keep the locations the same. So now I have the top left corner. If I permute it to the center of the image, it will now get a different position code.
But you need to add some extra constraint to make sure that the numbers are in the correct order. Make sure.
So
check they are reversed.
we'll see in a second what we are doing with this position coding. So one option that we saw last time is that the position coding is fixed. We have these sinusoidal patterns that actually depends only on the position in the sequence. And this way you encode the position and it's fixed. And the network learns how to utilize this information. We can also start with some random patterns and let the network learn what's the best way. And we'll see an example here. But the important here is that the position encoding, it doesn't depend on the data. It only depends on the position. So it can either be a fixed function or it can be a trained one. But its sole purpose is to encode the position of the token. So to prevent this permutation equivariant to kick in. Yes.
So in this example, each input is an unraveled patch with a.
Yes, it's a non-overlapping patches, and each patch, all the patches are projected using a linear projection. It's the same projection for all the patches. And then a position encoding is added. You can think about it as a convolution with the kernel size of the size of the patch, and the stride of this convolution equals the size of the patch. Good question. Because they decided so. In this seminal paper, an image is worth 16 by 16 words. It's an arbitrary decision. We have a problem with large sequences. So if you overlap the patches, you have significantly more patches. And they show that you don't really need them. So for tasks like classification, it's enough to look at non-overlapping patches. If you want to do some more refined tasks like detection and segmentation, you might want to consider other alternatives. Okay. So what vision transformers are out there? So this is like a basic architecture, and then we can decide on the number of layers we want to have in the architecture. So it's the same block, but we can have as many as we want. So people goes with either 12, 24, 32. The width is the dimension that we project the tokens to. So because of the skip connections, because the way the architecture is built, we have a single dimension. It's not like in convolutional network that we have lower dimension number of channels in the in the shallow layer, and as we go deeper, we increase the dimension. In transformers, we work with a fixed dimension. The attention is a multi-head self-attention, as we talked last time. So we have at each layer, we compute attention based on several learned projections to enable different concepts of similarity. And the number of parameters grows accordingly with the number of layers and the channels. But as you can see, the number of channels doesn't grow rapidly. It's like in convolutions that we only train parameters at the size of the kernels, and doesn't scale with the size of the images. So the same goes for transformers. The computations do scale with the image size, like in convolutions. For comparison, so we talked about ResNet architecture. So ResNet architecture is around 25 million parameters. So it's even smaller than the ViT base. On the other hand, the VGG network that we saw has almost 140 million parameters, which is somewhere between the base and large. Okay, and the naming convention that you'll see in papers that uses transformer architecture. So ViT is the vision transformer. The letter B stands for the size, either base, B, L, or what's the next one? Huge, and I think this is roughly it. The number says the patch size. So ViT B16 means we have a base architecture with patches of 16 by 16. You can see ViT base with patch of 8. Sometimes there's patch 14, 32. This is roughly the numbers you can come across. Okay.
Does the patch size make a difference?
Yes, it controls the granularity and the resolution of the transformer. So if you have smaller patch size, you have more patches more computation because you have larger attention matrices, but then you have features at a finer resolution. So if you want to perform tasks like segmentation and correspondences between images, you would be aiming at a smaller patch size. If you want a transformer that is more lightweighted in terms of computation, you would pick a larger patch. So you pay once by projecting very large patches into the embedding space, but then you have a very short sequence, and all the other computation will be very quick.
The embedding space,
So the embedding space is the space here. It's the dimension of the features. So the patch size determines how many patches you're going to have, because we usually work on a fixed size input images. So the bigger the patch, the fewer patches you're going to have. On the other hand, the width of the transformer determines the dimension of these patches. So in ViT base 16, the width matches exactly the dimension of the patch, but it doesn't have to be that way.
so an embedding of a 2x2 patch is going to be the same size as an embedding of a 4x4 patch?
You won't work with these small patches.
Whatever.
Yeah, but
16,
yes.
16 and 32, okay.
It's a design choice. There doesn't have to be a correlation between the patch size and the embedding space, the dimension.
Understand.
What is the patch size?
The patch size is the size of these tokens. So we took the image, we broke it into.
What is the typical patch size?
So typically people work with 16. But you can find 8, you can find 32. Sometimes people work with 14 because traditionally ImageNet images were resized to 224 by 224, which is 14 times 8 times 14 times 16, I think. But there's 7 somewhere in the number, so that 14 does make sense. But yeah, it's quite arbitrary, and you can train whatever you want. I'm working on a project now with the patches. I'm working on a project with 5x5 patches and 4x4, but in most cases, when you download or when you read the paper, you'll see we're using ViT B16 or ViT L32, things like that. Let's move on. So in their paper, they trained transformers on a very large data set of images. At the time, it was considered like huge, 300 million images. Now it's considered moderate. And then they fine-tuned on a small data set, which was the 1 million ImageNet. And they showed how performance scale, so with data that was used to pre-train the network. And as you can see, they used larger models and got better performance on ImageNet 1000 when they fine-tuned the model. So basically what they showed is that the transformer is very scalable. It can process huge quantities of data, and it profits from it. It gets better, and as it sees more and more images. Even if it sees 300 million images, it still learns and improves over seeing only 1 million images. So this is a very nice property of the architecture. It doesn't seem to have like a bound.
This is also a caveat, you need to have huge data
Not necessarily. So even if you train only on ImageNet, you still get good performance. So it's not that you benefit from more images, but it's not necessarily that you must have it. It's wonders of deep learning that you don't overfit, and you actually you have some implicit biases in the training process and in the architecture that actually guide you into these good solutions. So let's talk about some properties of the transformer. So what is going on in different parts of the architecture? So we saw with Tali how to visualize different parts of a convolutional neural network. We'll try to apply similar tools and inspect what's going on in a trained vision transformer. So we have a transformer, we trained it, we fixed the weights, and now we try to inspect what's going on in different components. So we can first observe what's going on in the embedding layer. So the embedding layer is simply a convolution layer that projects each patch into a higher dimension embedding. So we can actually view these filters, what these filters capture. And if we look at these filters, we have a lot of channels in this projection. The number of channels equals the number of the embedding dimension of the transformer. But if we show these dominant components of this projection, we see that it actually learns these nice blobs, these edges, colors, horizontal edge, vertical edge, diagonal edge, and we have some patterns that are more complex as we go to less meaningful components. And this is actually quite reassuring because if you recall, these are the kind of filters that AlexNet architecture has in its input layer, which also resemble these these oriented edges and color blobs. So this is kind of a sanity check, reassuring that the embedding actually corresponds to something that is visually meaningful. Yeah.
The training is part of the net or separate?
The
training the filters is part of the net or separately?
It's a single network. The network has an embedding layer, which is how to take image and break it into patches and project them, and then the transformer blocks. So this is part of the network. So you have the embedding layer, you have the position encoding. It's all part of the network. The main processing part, the transformer blocks, the nice thing about it is that it's identical to what is used in natural language processing. It's the same architecture. This is like a big change, conceptual change. So if before transformer, people used recurrent neural network and LSTMs and whatever to process sequences and convolutions for images, and there was no overlap between these two domains. Now that everyone are using the same architecture, suddenly ideas and training paradigms and things like that really flow between these two seemingly different domains. So this is nice. You're actually using the same tools and all the communities contributing.
The embeddings of a language model, how does that work?
So I don't think you can visualize embedding of language model. We talked about these embeddings last time. So you have like discrete tokens, and then you learn some embedding into a higher dimension, and then I don't know, you don't visualize, you can actually try to translate them. So a very famous way of projecting was word2vec that showed that they actually project words into some feature space, and then you can do some arithmetics in that space. So you can take the word like London, subtract Paris from it, and then add England, and you get France or some or similar embedding. So it was a very interesting property for this kind of embedding, but there's no visual there. Okay, so this is the embedding layer projecting patches into tokens. Let's talk about the positional encoding. Some architectures use fixed 2D position encoding. But in this work, they try to train the network to learn the position encoding in order to see what it learns. So they took us the patches, they added random noise. They started with random noise, different noise for each and every one of the patches, and let the network learn these patterns. What is the best pattern to learn for each position? So we can look at what the network learned when it was trained on 2D sequences. So at this point, the network doesn't know that the sequence is two-dimensional. It doesn't know that there's some spatial arrangement. It only knows that there is an order, some order for these patches, and needs to learn how to best encode this order.
When you say different noise to which patch, it's different formula of noise?
No, you have like you have patch size. For instance, in this example, we have ViT base with patch size 32. So you'll have 7 by 7 patches. So you have noise size 7 by 7 by or 49 by the feature space, which is 700 something. And this is like a block of noise that you add to all the projected patches.
From the same distribution.
Yes, it's normal something. I don't remember how they initialize it, but you propagate gradient to it as well. And then you can observe what patterns were emerging in this noise. And if they correlate each one of these patches with all the others, we can get these 7 by 7 correlation maps for each and every one of the tokens. So if we take the noise that correspond to this upper left corner and correlate it with all the position encoding, there's no image here. It's only the position, the learned position encoding. We can see that it matches itself, of course, at the corner, and it has some, it attends more to the row, the corresponding row and column. And we can see that this axial attention emerges at all, for all the positions that were learned. So it actually learned that there is a two-dimensional ordering of the sequence, although it never observed a two-dimensional sequence. So this is again a very nice reassuring property that emerged from the training of this transformer. Yeah.
Can you go over how they generate the position embedding again?
Yes. So we have an image, 224 by 224 pixels. And this is ViT base patch 32. So we break it into 32 by 32 patches, and we have 7 by 7 of these. So we have 32 by 32 from 0 to from 1 to 49. Okay, and we have these projections that we saw before, these nice edges and things like that. So each of these is embedded into a vector of dimension 768. So we have 1, and so we have 49, we have 1. So these depends only on the patches. They don't know anything about where in the image they came from. And if we shuffle them, we have the transformer will think the input is exactly the same, but it will correspond to a shuffled image, which makes no sense. So for each and every one of these, we add these random at first. This is random. This is 1. This is random 1, and this is random 49. So we have 49 random vectors. We initialize them randomly. They are different because we draw them from the same distribution, but they are different. And we propagate gradients to them. So there's some weights here that gets gradient to know how to better project the image patches. And there are some gradients that tells us how to fix these patterns, so we better know how to utilize the information about the position of the different patches.
See, so it's only initialized to be random once. And then
Yes, and then gradients are propagated, and what we are seeing here is the result of these trained position encoding. So what is the best way, optimal way of encoding the position of each and every one of the vectors? And if we ignore the information from the image and we only look at this position encoding, and now we look at the correlations between them, this is what we see. Okay?
How is it more beneficial than using the fixed positional encoding?
It's not more beneficial. You don't have a lot of extra parameters. And it's only propagating, it's like the bottom layer. Gradients don't propagate from here any further. So I think nowadays, I think it's about 50-50 when you read papers, if they train the position encoding or use the fixed one. But
maybe by chance, sometimes it improves slightly.
I don't think it makes a significant difference. I don't remember seeing a comparison, but I think the main point here was to show that it actually learned something that is two-dimensional. It's not trivial that it actually pulled it off. Okay. Next, so we talked about the embedding the input layer. Now we can talk about the attention heads inside these blocks. So we have an image, we project it, we add the position encoding, and now we process it, and we have the attention between all tokens and inside a layer. And we can actually look at these attention maps. So for instance, if we take this image of buttons and we look at this patch in the image, and we ask ourselves, what is the attention map that corresponds to this patch? How it attends to all other patches in the image. And we see that it actually attends to the labels of the buttons. And if we look at the banana patch, it attends more to the bananas, and a bottle patch attends to the bottles. And again, if we have zebras and elephants in the safari, zebra patches attends more to the zebra, the elephants attends more to the elephant, and they attend more to foreground rather than background patches.
There you're using a huge amount of patches, right?
Yeah, the resolution there, I think it's patch size 8, if I'm not mistaken.
Also, what happens with the patches, like inside the patches? So far it feels like you're doing the attention result happening between different patches, right? But what do you do with like with the pixels?
In the MLP layer? So
yes.
So in the multi-head self-attention, you actually break the vector into segments, and each segment goes to a different head. And then you concatenate the output of the different heads into a single vector. So it's chunked.
And you do MLP, no MLP?
And you do MLP on all the vectors just to shuffle the information. So if I have an information from one head that says, okay, I think you should attend to foreground object, and what do you think given the foreground? And then you have another head that says, attend to things that have similar color to you. So you have these informations in two different regions in the vector. Now you have an MLP that says, okay, I'll take all this information and use it together. Now, what you learned from the foreground, what you learned about similar colors, and I get a better representation that represents you. I don't have any visualizations of what's going on inside these components.
No, but the thing I don't get is one of the main steps in going from MLP to convolutional neural networks was getting rid of extra parameters that we don't need.
So the MLP here is not on the entire image. It's like a one-by-one convolution because you apply the MLP on each vector separately. Okay, that's
Explain that again.
so the confusion here, I think, is that in convolutional neural network, you had an image, you had conv layers, pooling, and then you had some channel by H by W features. And then you had an MLP that took all these features and made a prediction. So the MLP looked not only on the channel dimension, but on the entire chunk of the image. But now, the MLP and the transformers, we have a token, we have a sequence of tokens, we have a tension that actually mixes all the tokens. The MLP here works on each and every one of the tokens separately. There is no mixing of information. So if we have d-dimensional n tokens, the size of his MLP is d times d, the weight matrix, because it operates on each token independently. Here, the size of MLP is h by w by the output dimension. Are we clear about this difference? Yeah.
So if you have like multi-head tension, did you look at the like each patches, like some of all the
So it processes each patch independently. So we project it from D to some 4D, and then from 4D, I think it's 4 back to D.
So, but I guess I'm asking like if you have multi-head attention, you have like multiple patches that you output, right?
So in multi-head self-attention, each patch is processed through different attention heads.
Mhm.
And then you have the output of these different heads concatenated. So each head gets n patches as input and output n patches. So there is always one-to-one correspondence between the number of patches that were in and the number out. And if you have multiple, then you can take the output corresponding to the same patch from all the heads and concatenate them.
Okay.
And then you have like a single vector of dimension d, but this chunk came from head 1, this is head 2, this is head 3, and so on. So it's there is no integration of the information between the different heads. And then the MLP mixes all of it together in the same token without knowing what's going on in the other tokens.
Thank you.
Yeah. So far, we talked about the patches, the tokens that corresponds to actual image patches, but we have this special global token, the class token that actually asks the question, what's in the image? How does this token looks like? So we can look at the attention maps of this class token to the entire image. Where is this token draw its information from? And if you look at the attention maps, what do you see?
Just where the label comes from.
It really knows to attend. This is from the very last layer of the transformer. It really knows where the foreground is. Where is the interesting object in the image? So it's again, there was no supervision for this. The only supervision was class label, the output of the entire image. Like a very global prediction, and yet the class token was able to focus on this, on the foreground in the image. Yes.
So if we train a like a classification model, we get a segmentation model for free.
It's
Like
it's
like
almost a segmentation model. It's not for free, yes, but you get like a very good estimation of foreground. It's not perfect, but yes, it's get extra information. You had a question? No problem. And this model was trained on natural images, dogs, cats, animals, planes, things like that. And the nice thing about it that it's very robust. So we took, in another project, we took this transformer that was trained on ImageNet, and we applied it to X-ray images, as you can see here. And these X-ray images are out of domain, and they have a very poor dynamic range. So they are not very well normalized. There's some pixels that are very bright, some that are very dark. The gray, the spectrum is not utilized very well in many of these images. So we wanted a method that would help us normalize the intensities in the relevant part of the images. So we took out of the box transformer. These are the attention maps that we got in these columns. And if we threshold them, we didn't get a good segmentation. It's not something that you can say this is a foreground segment, but it was a good enough estimation that enabled us to focus on the relevant region and normalize the intensities for this image, and got a significant boost in performance in downstream tasks. So this was a very nice property of these emerge attention to the foreground by the class token. This is the attention. What about the logics that were learned by this model? So we have ImageNet classification, we have 1,000 classes, and we can ask ourselves, each and every one of these neurons that correspond to a class, what pattern, what it looks in the image, what are the images that actually activates this neuron, makes it think that this object is in the image, this class is in the image. So we utilize these methods that Tali showed in the previous class, and we can actually search for an image, a natural image that actually excites this neuron, this class matching neuron. So for instance, if we look at the class for goldfish, these are the kind of images that actually makes the model really excited about goldfish. And we can see that there are goldfish here. The colors for the foreground, for the background, at different scales, at different positions, different orientations. There's no like a clear fixed goldfish, but just like Play-Doh of a goldfish. And if you go for this bald eagle class, you can see the white head, the black feathers of the wings. You can see that it's sometimes in the sky, sometimes on the tree. And you see the textures of the feathers, which was very nice to see. And again, if you go for the collie-coated retriever, which is a type of a dog, I'm not sure you can see that you see the head and you see the curls in the fur of the dog. So you don't get like a fixed image of a dog, but you get some arrangement of the body parts, the textures, and things like that. So it has a very flexible way of representing this complex pattern.
You do see a lot of the backgrounds in these images, but when you look at those attention maps, seems like the attention was very much in the foreground, so.
So in early layers, there's actually the class token attends to the background in the very first layer because it needs to see some context. Classifications may change if you change the context dramatically. There's this famous examples of dogs versus wolves. I don't know if you're familiar with that. So people show that they trained a very good classifiers of dogs versus wolf, but then when they did GradCam or some other visualization, they actually showed that wolves usually were photographed in the snow with white background, and dogs were usually photographed in the summer, green and indoor. So the model was actually looking at the background to decide whether it's a dog or a wolf. It didn't look at the animal almost at all. So
Very good classifier for the telling winter from summer.
maybe, yeah. So yeah, background does get into it. So we saw in the with the eagle that you sometimes want sky background, sometimes trees. So the background also is taken into account, but the object plays a more dominant role, as we saw with the attention. And again, we have classes that are not that are scenery, like a volcano. And again, you see the eruption, you see different the colors and the textures that match this this class. And I think this is a good time to take a break, and we'll reconvene in 10 minutes. So okay, so we saw what's going on in the trained projection that was trained to classify the images, but we want to go deeper and see what's going on in this class token, what it looks for in the image in different layers of the transformer. So we can look at the very first layer and ask what are patterns that activates specific channel in the class token. And we see that it actually looks like blobs of colors, not very meaningful. So a specific channel in the class token in very early layers doesn't look for much, just random colors, not random, but specific colors in the image. If we go slightly deeper to layer 3, we see some emergence of textures. And this is somewhat like the hierarchy of representation we saw in convolutions. If we go slightly deeper, we get these kind of more elaborated object parts. And this is kind of like Rorschach stains. So it's, I really project a lot of my beliefs on these. But if you go slightly deeper, we can actually find neurons in the class token that are activated by dogs, and dogs were really, really dominant in ImageNet dataset. I think about quarter to third of the ImageNet dataset is dogs. So it's not surprising that we have some dog representation in there. But again, it's not really clear why and how these patterns emerge inside the model. And I think for me, it's very curious to investigate further what's going on inside this model. Let's talk about the receptive field of this network. So in convolutions, we saw that the receptive field of a specific neuron is just the size of the kernel. And if we have a stack of convolution layers, then the receptive fields grow gradually. What is the receptive field for the transformer?
It's still like the whole image.
Theoretically, it's the entire image, because we have attention that each patch attends from the very first layer to all other patches, then effectively the receptive field is the entire image, the entire sequence. But there's the notion of effective receptive field. What is the actual weight of each other patch on the output? So in convolutions, the pixels that are right under the center of the convolution usually contribute the most, and those at the periphery only contribute, so they affect the output, but they only have marginal effect. So if we measure the weight of attention for each pixel based on the distance from that patch, we have this plot. So we have x-axis as the depth of the network. These are the early layers, early transformer blocks, and these are the final layers. And this is the mean distance in pixels of the attention map. So we see that in early layers, some of the heads only attend on average to very local patterns. And only very few heads actually look farther away. So the effective receptive field at this early layer is not in the entire image, but it's something that is slightly smaller. But as we go deeper, almost all heads attend to the entire image and basically have global information, and they can ask global questions about the content of the image. So they are not restricted to anything that is nearby them. So theoretically, all the layers have access to all the patches, but effectively, they only utilize this power at the as the layer is deeper in the network. So at this point, we can conclude the first part of the course where we learned about different layers in deep learning, different architectures, and all other basic concepts that we have. And we can actually do some comparison between convolutional neural network and transformers at this point. So we have an image of a dog, and for this visualization, what we did, we took a few dozens of images of animals, facial animals, and we extracted features from different networks, from a CNN, from a ResNet, which is a CNN convolution neural network, and from a vision transformer, both trained and fixed. And we compute PCA over these features, and we visualize the features of the different layers of the network. So if you look at the convolution neural network, we see from a shallow layer to a deeper layer, and the first component of the feature is shown at the top row, and the second, third, and fourth as RGB colors in the bottom. And we see we have a very high resolution of the features. And we see that they respond mainly to local patterns in the image, edges and blobs of textures. And as we go deeper, what happens to the resolution of the feature map? Decreases because we have pooling layers in the ResNet architecture. But we see that it gets more and more specialized. So for instance, the eyes has the same color, meaning that they were mapped to the similar region in the feature space. And there's no more sensitivity to local patterns, but more of global patterns like the dog, the face, and things like that. So as we go deeper, we pay by lowering the resolution, but we gain by more semantic information in the features. Okay? Convolutional neural network. So this is a specific ResNet, but this kind of behavior it can be found in other type of convolutional networks as well. What about the transformer that we just saw? So as we go deeper, the resolution stays the same. But what do we see at the very shallow layer? What are the colors here?
It's gradient.
It's the sequence, it's the position. Yeah, so we see left, right in the dominant, and then we see these kind of up, down in the bottom. There is some signal that comes from the patches under it, but the most dominant information here at the very early layer is the position of the pixels.
Where's the direction of flip?
What?
Where is the direction of flip from?
This is different components. What I'm showing you is different components of the features. So there's one component that looks horizontally and the others looks vertically-ish. Notice that you don't have this kind of position information in convolutional neural network because convolutions are translation equivariant. They don't store position information. And as we go deeper with the transformers, the resolution stays the same because we don't change the number of tokens. The position information decays as we go deeper, and we get more and more semantic information from the features. So we have the same localization of eyes, mouth, the dog here, but we don't pay in resolution. We get very semantic features, but they are still very well localized because we have many of them. We don't lose resolution. Okay? So let's see different properties of convolutions and transformers. So convolutions maintain the 2D structure logic of the image by applying rectangular convolutions all over the image, and the features stays the same in the same shape through the processing. So the very structure of the feature space maintains the 2D structure of the image. In transformers, we break this structure by transforming the image into a sequence of patches, but thanks to the position encoding, we have this information preserved in the transformer. So it still knows that it's processing a two-dimensional signal rather than a one-dimensional sequence. What about shift equivariant? So convolutional neural networks are shift equivariant. If we shift the image, convolutions are shifted in the same manner. Do we have shift equivariance in transformers? No, we no longer have this because transformers actually have positions. If we shift the image, the position would change. The position encoding information would make us sensitive to this kind of shift. And as we saw in the features, this kind of position information is really present in the features, especially in the early layers of the transformer. Local correlations, local patterns. What do you think?
Yes, for CNNs, no for ViT.
Exactly. So in CNNs, we consider local patterns, and as Asaf showed, this is very advantageous because we can build this hierarchy of representations. We don't have that in the transformers because we have attention to the entire image. We have an hierarchically growing field of view. So yes, for convolutions, because we have this hierarchy of convolutions and pooling. And in ViT, we have attention to the entire image theoretically at the very early, but what we saw that effectively this is not always the case, but this is something that emerged out of the training. And we're not sure whether these two are actually a good property of CNN or bad properties of ViT. And hierarchically growing complexity of the representation, and this is something that is in both cases. So in both cases, we start with considering local patterns, local textures, edges, and we saw that these representation gets more and more complex as we go deeper, both in CNN and transformers. And in both cases, we have a reasonable amount of parameters, because we only consider projections of local tokens or local kernels of features. And the number of parameters doesn't depend on the size of the input in both cases. And a global representation of the input. So in CNN, do we have a global representation? We can have one artificially by average pooling the features, but we don't have one that is built into the architecture. While in Transformer, we have the class token that actually stores some global information about the image that we are processing, which can be very nice. Let's talk about some more properties of the transformers. What happens if we drop some patches from the input image?
If they contain relevant information, then you no longer have this information. So they won't like have that as it goes through.
Okay, so if we drop patches, we simply skip them from the input sequence.
This is in the training.
You can do it in training. You can do it during inference. So you have a trained sequence and you simply drop patches. And then instead of having n patches, you have n-2, for instance. But since the transformer doesn't care about the sequence length, it can work with any sequence length, it doesn't affect the processing. It's only some of the information is missing. If we were to do this drop with a convolution, how could we do that with the convolutional neural network? What?
Replacing with zeros.
So replacing with zeros won't be equivalent to drop the patch, because now you have a convolution kernel that goes from image pixel to the zeros. It actually sees zeros. There's something black there. The transformer, if we simply omit these patches, won't see any black patches. So convolution sees an image with black patches. The transformer just sees a shorter sequence. And if we know to adjust the position encoding, not to mix between these encodings, it will know which patches are missing and which it has. So this is a very easy way of doing some efficient processing if you don't want to process all the image. It's a nice augmentation during training. And actually, transformers are quite robust to this. So if we take an image and we randomly drop patches, so this is what the transformer sees, which actually sees only part of the image. We can even do this drop like very adversarially, like dropping patches that we know that are important. And we can do this the other way around by dropping patches that we don't think they are. And we can actually measure what's the effect of each policy on the prediction of a trained network. And what we saw is that for transformers, which are the dotted lines here, we can drop significantly large amount of information and still be able to get high accuracy on classifying the images, while in convolutional neural network, this is the red line here, even minor drop of patches, even at random, degrades performance very rapidly. If we actually do this adversarially and drop the significant patches, then even the transformers are hit by this drop very rapidly, but not as fast as the convolutional neural network. And if we drop only background patches, non-salient, then we can actually drop a significant amount and still be able to classify the image correctly. and think about the efficiency of this method, we can process a very small portion of the image, get a good classification, and do it very efficiently because we pay quadratically with the number of patches. Okay, so this is a hint of efficiency that can be gained. But again, this is kind of chicken and egg because you need to know what's in the image in order to know which patches to drop. So it's a theoretical bound in a sense.
Can you compare this patches to the dropout in
So dropout doesn't save you computation. You just zero out some neurons during the processing, and you don't eliminate entire features in the feature map. You just eliminate some neuron at some random points. This is like dropping a portion of the input. But you drop the entire patch for all the image. You drop out, you randomly shut down a neuron somewhere in the network. So it doesn't really save you computation, and it's more as an augmentation during training. This you can do during inference as well. So this is actually during inference.
I'm asking if this would be efficient also as an augmentation.
Yes, so we can do this patch drop for efficiency, as we said. We can do this as an augmentation to train the network to be able to classify given only portion of the images. And also highlights how much redundancy we have in images. So an image is worth 1,000 words, but you don't really need all the patches in the image. A lot of patches repeat. And if you're taking the Introduction to Computer Vision course, we'll actually talk about it Sunday, I think. So some other properties of vision transformers is that they are very data hungry. As we saw before, the larger training set, the more augmentations we have, the models learn better representations. They don't saturate, performance don't hit like a cap. So you can have bigger model. The more data you have, training data, you can train bigger models, and the performance will grow. They can actually encode all this information. They are relatively robust to adversarial examples. I don't have the numbers here to show, but again, there's no complete robustness, but slightly more than convolution.
The first property doesn't hold for CNN.
So CNNs tend to get to some. So if for a specific architecture, if you increase the training data, at some point, the test performance would hit some ceiling. The transformers, what we showed in the first part of the lecture, the graph that you increase from ImageNet 1000, ImageNet 21K to this 300 million data set. Performance kept growing for the same model, which
Okay, and even if we will do the CNN, like
so if we grow the architecture, yes. So if you grow the architecture, then it will be able to represent more data. But with transformers for a fixed architecture, it takes a lot of data for it to get to saturation. And there's shape texture bias. So for instance, if we have this texture image and we let a convolution neural network to classify it, it will classify it correctly as elephant. If you give it this nice cat image, it will say this is a cat. But if we do this mixing of a cat with a texture of elephants, convolutional neural networks would usually prefer to give a classification based on the texture. While transformers not necessarily have this kind of bias toward texture. They will also look at the shape of things, which is a nice property. And if you think about it, convolutional neural networks are actually matching patterns in the image. Texture are easier to match. They are easier to define as pattern rather than shapes that they are not specific patterns, especially deformable shapes like cats, dogs, and other objects that we know. Which time do we have? Okay. So we saw the vision transformer. We take an image, we break it into patches, we get a sequence. Once we have a sequence, we can use transformer to process it. This is great. Nice properties. Everything is perfect, right? But we have one slight problem. What is the complexity? So with convolutional neural network, we have an input X, and we have a kernel, and the number of operations we need in order to convolve an image is proportional to the size of the image. It's O of n. But for transformers, because we need to compute the cross attention between all patches to all patches, complexity grows quadratically with the image. So if we have twice large image, it will take us twice the time for a convolution, but 4 times the memory for a transformer. And this poses a huge bottleneck on the image resolution we can process, the sizes of GPUs that we need in order to do this. So the efficiency of this computation is a bottleneck for the visual transformer or transformers in general, this architecture. So what can we do about it? So this is an overview from a paper about efficient transformers. So as you can see, this is like a really acute problem because many people are trying to solve this. And there's a lot of methods that are trying to solve this problem. And what you usually see when there's a problem with so many solutions, the first thing that comes to mind is that none of them actually nails it. Because if there was one good solution, everyone would converge to that one and forget about the others. So there are a lot of approaches and things and ways to try and tackle this n-squared complexity. And we'll touch upon some approaches, different approaches to this, and I'm going to survey it quite fast. So one way of tackling this n-square attention is to make it sparse. We saw that we can drop patches and still get good performance. Maybe we can do the attention in a more sophisticated manner and not attend to all the patches. So if we have a sequence and we have full attention, so each patch attends to all other patches, or if we have temporal dependency, so each patch attends to all past patches. But we can think about different patterns. So you can have attention locally to tokens that are nearby you. So this is example that comes from text sequences and not from images. So this is a 1D example. And you can have this strided attention that you go on a fixed path or like this axial pattern. And if you have this kind of patterns, then you have not n squared, but n square root of n, which is much better. And still, the damage in performance is not that big because you have multiple layers of attention. Information does propagate between these local and strided attention and kind of works. And you can think of other kind of sparse attention. For two-dimensional data, you can think about axial attention. So for each query, it attends to the same row in the image and the column. So in one layer, you attend to whatever is in front of you and below you, and the next attention actually propagates information, and it goes through this axon layer between all the patches. And again, this is n square n. This was kind of forcing some sparsity on the network. We can also think about other structures in the attention matrix like low rank. So the attention head actually computes a softmax of the query times the keys time values. And actually we have, if n, the number of tokens, is smaller than the dimension, then this matrix multiplication is actually of low rank. And if we ignore for a second the softmax here, we actually have this matrix multiplication, and we can do it instead of multiplying Q by K and get a huge n square matrix. We can start by multiplying the K with V and get this very small K transpose V matrix. And then at no point we have this large n by n square attention. But we do have this attention, this softmax in the middle that prevents us from this very efficient computation. But effectively, we can look at the rank of the matrix as we go deeper in the layers, and we can look at these eigenvalues of the of this matrix, of this attention matrix. And since we don't have time, I won't go into details of this plot, but what it actually shows is that effectively the rank is very low. And if the rank is effectively very low, we can actually learn projection matrices, E and F, to make this computation more efficient. But then we are committed to a sequence length, because these matrices depends on the sequence length. What it actually does, it projects an n length sequence to K representative tokens and compute the attention only in this K dimensional space. So we have only n times K, which is smaller than n. And if we look at the scheme of a multi-head self-attention, it amounts to learning these E and F projection matrices in the process. And if K is sufficiently small and fixed, this complexity turns to O of n. We can think of other methods like decreasing the memory by downsampling. So maybe we don't need all the features, all the tokens in the input. Maybe we can learn somehow to represent all the tokens by a fewer number of tokens. And in this work, they learned a specific projection layer that actually says which are the important tokens in the image. And it learns a map and combines all the tokens based on this map into a single token. And it learns how to map these tokens, and it doesn't, it learns a few of them. So for instance, it has 8 such projections, different projections. So we take a collection of tokens and we project them to a fixed number of tokens. And then we do all the processing on this fixed number of tokens. So instead of having 16 by 16 or 14 by 14 tokens for an image, we now have 8. With 8 tokens, you process very efficiently and get very good performance.
How do you know which token to choose?
So they trained this layer that actually knows how to choose. So they trained 8 copies of it, so it chooses differently. So it has different information in each one of these 8 tokens. But as we saw before, if you know how to drop the tokens, you can actually get very good performance by dropping 80% of the tokens. So this is actually something along these lines. So they learned how to, where are the important tokens? They merged them. They didn't drop, they averaged them into these specialized tokens. And now they have all the information there, and they do the processing on a fixed size and very small number of tokens. And they can do it for images and for videos, and they show nice performance. What if we don't want to discard tokens? We want to do tasks like image segmentation, when we want localized information, and we don't want to attend to all features. So SWIN's shifted window transformer was an architecture proposed for semantic segmentation and detection, where we need this localized information. We don't want to discard tokens. So we can look at the image, and we have patches, which are these small rectangles, but we can look also on local windows. So we cannot afford to compute attention between all the patches because we have many of them in images. We want to do segmentation. We want to work with high resolution images. So we can only afford to do attention within these local windows. So if we were to process image like that, what would happen in a transformer? So we will be able to process, because now the attention is only on a fixed size sequence, but there's no propagation of information between these windows. It's like processing 4 different crops or 4 different images. This patch will never know what's going on down here. So what they do is that they shifted these windows between the layers. So this is one layer. The next layer will shift the windows in this half stride manner. So now this patch attends to patches from this window. And actually, after 2 layers, information can propagate between all patches in the image. And they borrowed some other concept from convolutional neural networks. So they have this block structure where they have different granularity of patches. But in each block, they have this shifted window attention to process the image. So they have blocks, different granularity, different dimensionality, unlike the transformer. But the main processing unit here is, again, attention rather than convolutions. And they showed nice performance on dense prediction tasks like segmentation and detection. And again, if we compare processing images using transformers, we see that the number of parameters is fixed, but the number of computation grows significantly as the image size grows. But with this shifted window, we can process images in different scales. The number of flops, number of operation scales nicely. It doesn't explode, and we get very nice performance in classification and in the number of images we can actually throughput through the network. There's also other ways we can tackle this problem of dense predictions. There's a work on multi-scale attention. So for instance, if we have a high resolution input image, computing full attention is prohibited. But what we can do is we can have a low resolution image, process it, and look at the attention of the low resolution image. And then based on the attention map in the low resolution, we can compute a sparse pattern for the high resolution. So now this would tell us how to attend the high resolution input image. So if we saw this one way of reducing complexity by these fixed sparse patterns, here we can change the sparse pattern based on the attention at a low resolution of the image. So to conclude, we complete this part of the course where you actually learned the building blocks of neural networks. So you learned about a linear layer that connects all the inputs to all the outputs. And this linear layer can be a building block in a more complex layers. And we saw this linear operation over and over again inside convolutions, inside transformers, inside recurrent blocks. So this is like the very basic building block. On top of this linear attention, there's all kinds of non-linear activations to prevent from the network to collapse to a single linear operation. You learn about a convolution filter, a convolution layer that actually process small patches of the image and take advantage of the translation equivalent property of images. For sequences, we saw the recurrent block that takes advantage of the temporal dimension and the temporal change in a sequence. And finally, in the last two lessons, we saw attention layer that proved very beneficial in processing sequence, but also for processing images once we convert them into sequences in the right manner. In 2 days, the next lecture will be on generative models, and Asaf will give it. Thank you. Any questions? Great.
Let's see.